All right, so let's look at the problems from section 6.1. So for these first few, I just wanted you all to get some practice on um, transforming some time domain functions into Laplace domain um, using the table. I mean, you can absolutely do the integral if you want, but I'll provide the table for you. So this first one here, to convert sine of a at, that is directly this row of the table. So that is going to be relatively straightforward. That's going to be f of s equals a over s squared plus a squared. So yeah, that one is pretty cut and dry. That one comes directly from that row. So moving on to number 2. So 2 cosine at minus 3 sinh at. So it gives us, these hyperbolic sine and hyperbolic cosine, sinh and cosh. But there actually is a line in our table for each one. So what is cosine at? So one thing we can rely on is this, that the Laplace operator is a linear operator, and that means two valuable things. And I'll kind of basically condense them into two things here. Let's say that I want to take the Laplace transform of a times f of t plus b times g of t. So I'm adding two functions together, and I'll also have a scalar multiple of both of those. Because the Laplace operator is a linear operator, then this is equal to this. It's equal to a times the Laplace transform of f of t plus b times the Laplace transform of g of t. So, informally speaking, that means that um, you can treat sums and differences and multiples the way that you probably expected, the same way you can't mean the integral is a linear operator. The derivative is a linear operator. Many of you are probably very used to when you take an integral, if you have a constant multiplied by a function, many of you probably just instinctively take that constant out of the integral, and that's totally fine to do because the integral is a linear operator. The Laplace transform is the same kind of thing. So because of that, I can do this. What is 2 times the Laplace transform of cosine at minus 3 times the Laplace transform of sinh of at, not sine hat, whatever. You know what I mean. Um, those come directly from the table. So the Laplace transform of cosine at is s over s squared plus a squared. The Laplace transform of sinh of at is a over, I lost it, s squared minus a squared. So one last move here, 2s over s squared plus a squared minus 3a over s squared minus a squared. So you don't need to break everything down into that many steps, but just wanted to explain why that's possible. All right, Laplace transform of te to the at. So is there a slot for this? More or less is a little bit halfway down the table. So I know that the Laplace transform of t to the n times e to the at is equal to n factorial over s minus a to the n plus 1. So in the thing I'm looking at, what does n equal? Well, I have t to the first power. So if n equals 1, then what do I have? I have the Laplace transform of t to the 1 e to the at. That's equal to 1 factorial over s minus a to the 1 plus 1, or 1 over s minus a squared. All right, so that is the Laplace transform of t e to the at. Now, so in the first three, we were doing taking the time domain function and transforming it into the Laplace S domain. Now we're going the opposite way. So now we're going to look at the right-hand side, the right-hand column of this chart, and go the opposite way. So what is the Laplace inverse transform of S to the power of negative 3/2? So do I see any terms like that? Do I see any S raised to the power of, something arbitrary? It's not jumping out at me. All right, so many of these entries, are pretty restrictive on what kind of inputs you can, or what kind of exponents you can have for S, or for S. One thing I'm going to do though is many of the exponents are, S is in the denominator. So I'm going to rewrite this first of all as f of S equals 1 over S to the 3/2. So, like I said, many of these, require you to have a integer value um, for your exponent. The exception I see is this fourth line down, which is going to contain a function that's kind of strange, but um, we'll talk about how to deal with that. So I'm looking at this here. The inverse function, or the inverse Laplace transform of this letter right here is capital gamma of a plus 1 over s to the a plus 1 is equal to t to the a. So now, based on what we have, what is our a? I think our a has to be 1/2. So if we plug in that 1/2 for a here, we have the inverse Laplace transform of gamma of 1/2 plus 1 over s to the 1/2 plus 1. Now, what the heck is that gamma? So this gamma function, it's kind of think of it as this, it's like the factorial function, but it's more generalizable. So the factorial function can only handle the positive integers and 0. The gamma operator can handle a wider variety. It can handle complex numbers, irrational numbers, rational numbers. So something I recently looked up is that the gamma value of 3/2 is equal to, oh, did that backwards. 1/2 times the, not f, you want it to be f, 1/2 times the gamma of 1/2, which I believe is 1/2 times the square root of pi. I'm gonna go double check that again just to make sure. What is gamma of 3/2? Yeah, Wolfram will tell you. Gamma of 3/2 is radical pi over 2. Okay, so that's what radical pi over 2. So yeah, this strange value here, radical pi over 2, which is all to say, here's what we have. We know that the inverse Laplace transform of radical pi over 2 over s to the 3/2 is what? It's t to the a, which is going to be t to the 1/2. But do we have, is this where we started? Not quite. We have radical pi over 2. So we know what the Laplace transform of radical pi over 2 over s to the 3/2 is, but we just have 1 over s to the 3/2. So we have to adjust here. We want to multiply our result by the reciprocal of radical pi over 2. So that is going to be this, 2 over radical pi times t to the 1/2, or yeah, 2 times the square root of t over pi. Yeah, this is probably a pretty cryptic thing, but yeah, again, I'm just trying to get us to like kind of suss out what rows of the table we want to use. All right, so f of s equals 2 over s squared plus 9. So something you'll see a lot of on here is denominators that are of the form variable squared plus a constant squared. So I see a lot of s squared plus a squareds here in the denominator. So I think if we set this up as, 2 over s squared plus 3 squared, that's probably going to be productive for us. So now we see lots of things that look like that, but which one do I actually want? Well, the sinh and cosh, those are differences. So I don't have those. So it's either going to be sine or cosine. So how do I decide between sine or cosine? Well, the numerator in sine is a constant a, and the numerator in cosine is the variable s. So I'm looking at a sine. So, but look at the way that's set up. Our value of a, we're saying, is 3. So if I use the table, or that row of the table, then my inverse Laplace transform is going to be inverse Laplace transform of 3 over s squared plus 9 is what? What is the other part of that? That's going to be sine of 3t. But I don't quite have that. I have, what's my numerator is 2, not 3. So I essentially have 2/3 of that. So because of that, I'm still going to have sine of 3t, but I have to multiply that by 2/3 to get the right, to account for the fact that I have 2 in my numerator instead of 3. All right, finally, this last one here. So I have 1 over s plus 1 squared times s squared minus 9. All right, do I see anything in here that has product of denominators? So s plus 1 squared. I doubt I'm going to find it. So here's what I probably have to do. I suspect I'm going to have to do partial fractions on this. So let's set that up. What's my skeleton going to look like? Well, first I think I can keep factoring. So 1 over s plus 1 squared times s plus 3 times s minus 3 and then how's that going to break down? It's going to break down into, I think, 4 factors. A over s plus 1. I'm going to take it to a different line. A over s plus 1 plus b over s plus 1 squared plus c over s plus 3 plus d over s minus 3. So, I got 4 unknowns to solve for. That's okay. So now, how do I keep doing partial fraction decomposition? I'm going to multiply both left and right-hand side by that full denominator. So what's that going to do here? That is going to give me this. 1, because all the denominators on my left-hand side cancel, equals what happens to each of these terms? A times s plus 1, s plus 3, s minus 3. I'm just going to stack them all up. Plus b times the s plus 1 squares are going to cancel, so I'll have s plus 3, s minus 3, plus c times s plus 1 squared times s minus 3, plus d times s plus 1 squared, s plus 3. All right, so how do I solve for 4 unknowns? That's so many. I think my preferred way to go after these is, I know the A, B, C, and D are constants. So what I'm going to do is I'm going to strategically pick values of s that make as many things as possible vanish. So I think if I choose, let's start with s equals 3. If s equals 3, then how does this equation look? Left-hand side is still 1. All right, but what happens if s equals 3? Well, then the stuff multiplied by a goes to 0 because of the s minus 3 term. Same with b, same with d. Or sorry, same with c. So that allows me to get d right now. So 1 equals d times 4 squared times 6. So that's pretty big. Is that legit? And s equals 3. 3 plus 1, 4 times 4, 16 times 6. So that gives me the d is equal to 1 over 96. All right, so I got one of my constants already. I believe I can do the same thing. Let's pick another value of s that makes sense. How about -3? So what vanishes when I pick a -3? I think I lose the a and b terms again because I have that s plus 3. I'm not going to lose the c term, but I am going to lose the d term. So now I have 1 equals -3 plus 1, so that's -2. So c times -3 plus 1 is -2 squared, so 4 times -3 minus 3, so that's -6. So that gives me that c is equal to -1 over 24. All right, so I got 2 of my constants. Now, what's a good value to choose again? How about -1? So if I choose -1, then basically everything but b should go away because they're all going to get zeroed out. So this gives me 1 equals b times -1 plus 3, which is 2, times -1 minus 3, which is -4. So then I get b equals -1 over 8. All right, unfortunately, there's no fourth value of s that I can plug in that's going to magically make everything but s or everything but a go away. Because I tried, look at its factors. Already did -1, 3, and -3. But here's the good news. I have 4 unknown constants, or I had 4 unknown constants, and I figured out 3 of them. So I'm just going to pick any old value of s. 0 is always convenient. If I say s equals 0, what do I get? 1 equals a times -9, so -9a, plus b times -9 minus 9b, but I know what b is. It's -1/8. Plus c times -3, so -3 times -1 over 24, plus d times 3, but that's Wait, what did I do here? Yeah, 3 times d, which is 1 over 96. So I have a slightly more complicated equation here, but I can still solve for a. So negative 9a equals 1 minus 9/8. 3 over 24 is 1/8, so minus 1/8. 3 over 96, that's minus 1 over 24. Let's rewrite all these in terms of 24ths. So 24 over 24 minus 27 over 24 minus 3 over 24. So 24 minus 27 is negative 3, minus 3 is negative 6, minus 7. So negative 7 over 24. That means that a is equal to 7 over whatever 24 times 9 is. $216. So strange constants, but we got them all. All right, so what have we done? We're doing that for so long, maybe we lost sight of what the goal was. Oh, I do have more room here. Good. So I was running out of it. So now we can rewrite our partial fraction here. So 7 over 216 all over s plus 1. Plus or minus 1 over 8 all over s plus 1 squared. Minus 1 over 24 all over s plus 3. Plus 1 over 96 all over s minus 3. Hopefully those are nice and easy to pluck out from my Laplace transform calculator. So this function is called capital F of s. So what is f of t going to look like? F of t is going to be the inverse transform. What is, I believe these all, or 3 of them at least, are going to come from this second row. 1 over s minus a is equal to e to the at. So I believe this first term is going to be 7 over 216 times e to the, a should be negative 1, so e to the negative t, minus 1 over 24 e to the negative 3t, plus 1 over 96 e to the positive 3t. Okay, so the second line of this table gave me all 3. Basically, it gives me the first, second, and the fourth term. So how do I deal with s plus 1 squared? Do I see that anywhere? S plus 1 squared in the numerator. I don't see anything with the quantity squared, so we might have to do some manipulation here, and that's okay. Okay, what I think we're going to have to do is to do some scratch work where we do some completing the square. So 1 over s plus 1 squared, that is equal to, actually, if we're just completing the square, yeah, I've already completed the square. So maybe I just need to realize that my b is this. So if I write it that way, then let's look at the e to the at sine bt line. So I have a constant b over s minus a squared plus b squared. I don't think that's quite going to work because I have basically if my b is 0, then that I have to have a non-zero b term. So let's try again. Okay, I think the one below it. So this line, t to the n times e to the at. So that n factorial over s minus a to the n plus 1. So let's think about this. What is our value of a? So this didn't do us any good. So we have this Laplace transform, inverse Laplace transform. The inverse Laplace transform of n factorial over s minus a to the n plus 1 equals t to the n e to the at. Now, for the thing we want, what is our n? Well, if n plus 1 is 2, then n equals 1. Our a is going to be equal to negative 1. So is that what we have? Let's try it. If I put a 1 in for my n's and a positive 1, I think this is what I have. I'm going to have to adjust for the constant, but I'm going to have to adjust for the negative 1/8, but that's easy enough to do. So n is equal to 1, a is equal to negative 1. So I think my final term gets adjusted or gets transformed to this, minus 1 over 8 t e to the negative t. So long way home for that one, but that is, I believe, our final transform. I'm going to go ahead and take a look at that last term one more time. So our inverse Laplace transform of 1 factorial over s minus negative 1 to the 1 plus 1 becomes t to the 1 times e to the negative 1t. That's all assuming 1's in the numerator. We had negative 1/8 in the numerator. Okay. So yeah, I feel good about that. So that's all for section 6.1.